Welcome to OA Week 2024. We will get started in just a moment. Going to give some time for people to join. Great. I think we'll go ahead and get started, and people will just be trickling in. Welcome, everyone. Thank you for joining us for OA Week 2024. Please note that this session is being recorded. My name is Catherine Brown, and I am one of the coordinators for OA Week. And today I will be moderating this session on technology gaps and new tools for ocean acidification research. Ocean Acidification Week, OA Week, is presented by 4 sponsoring organizations. First, GOA-ON, Global Ocean Acidification Observing Network. Second, NOAA, the United States National Oceanic and Atmospheric Administration, the Ocean Acidification Program. Third, the International Atomic Energy Agency, the Ocean Acidification International Coordination Center. And last but not least, IOC UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. Next slide, please. GOA-ON was established in 2012 with just a handful of members. Since then, it has grown immensely and now has over 1,200 members from 114 countries. It also consists of several regional hubs which span across continents and oceanographic regions. We'll be hearing from most of them throughout OA Week. We've already heard from some, and there will be a few more for the rest of today and tomorrow. If you're not a member yet, you can join GOA-ON today by visiting a link that I will drop in the chat. OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to COVID-19. Following the successful in-person symposium on the ocean and a high carbon dioxide world in 2022, and another successful OA Week in 2023, GOA-ON is bringing back OA Week 2024 to maintain momentum around ocean acidification research and to provide a virtual platform for the community to exchange their latest findings. During the presentation, all participants will be in listen-only mode. You're welcome to type any questions into the questions box, which can be found at the bottom of the control panel on the right-hand side of your screen. We'll be monitoring incoming questions and we'll pose them to our speakers during the question and answer section, which will begin immediately after the final presentation. For this discussion, you can also use the raise hand function in the toolbox at the bottom of the screen, and we will call on you to ask your question directly during the Q&A portion at the very end. And with this, I would like to start off this session by thanking our speakers and audience for participating in this session on technology gaps and new tools for OA research. Today's session will feature 4 presentations where researchers working on the development of new techniques and technology for the observation and measurement of ocean acidification will introduce their tools. Each speaker will provide around a 10 to 12-minute presentation, and we will hold all questions until the end for around a 30-minute discussion as a group. With that, I will introduce our first speakers. So I'd like to introduce from the University of Edinburgh, Murray Roberts and Gavin Sim. Murray Roberts is a professor of applied marine biology and ecology at the University of Edinburgh. He founded Edinburgh's Changing Oceans Research Group and led the EU Atlantic research programs Atlas from 2016 to 2020 and I-Atlantic from 2019 to 2024. He studies marine ecosystems in the changing ocean, focusing upon structural habitats such as cold water corals in the deep ocean. Gavin Sim is an environmental analytical chemist in the School of Geosciences at the University of Edinburgh, where he manages their analytical services facility. His background is in terrestrial water and soil nutrients and metal analysis, but over the past couple of years, he has been working with Changing Oceans Research Group to develop their ocean acidification capabilities. Murray and Gavin, take it away.
Thanks so much, Catherine, and great to be here today. I will just bring up my slide deck. All being well, you can see that. So Gavin and I are sharing the presentation today, and I will just give a little bit of context and background in terms of ocean acidification research at the University of Edinburgh, and then Gavin will get into the meat of our presentation in terms of how we've automated the analysis. We're actually really excited about this development and delighted to have the chance to share it with you today. A little bit of history, which I won't dwell on for too long because I think many people on this call know it very well, but certainly from my own perspective, I began this sort of work with EPOCA, the European Project on Ocean Acidification, in 2008 to 12, which of course produced its best practice guide, and then followed that with the UK Ocean Acidification Programme, which lasted up until 2016, and at the tail end of that, we edited an updated synthesis for the Convention on Biological Diversity on the impacts of OA on marine ecosystems, which had an ancillary benefit. It allowed us to then work further with CBD under contract to produce a voluntary specific work plan on biodiversity in cold water areas within the jurisdictional scope of that convention. And that said a lot about ocean acidification. It said a lot about monitoring. I'd like to come back to that on my next slide. And then, as Catherine's mentioned, one of our kind of directions of travel has been through European framework funding to allow basin scale analysis of Atlantic marine ecosystems, and OA and temperature change and climate drivers of ecosystem change have been fundamental to both Atlas and Atlantic, where certainly in the last few years we've been focusing on what does this mean to the structural integrity of things like deep sea coral reefs, which are in many cases composed primarily of dead coral skeletons which feel the effects of corrosive seawater very rapidly. They become porous, brittle, lose their structural integrity. So I mentioned the CBD work plan, and I think it's interesting to pull out some of the information in here. And remember, all parties to the CBD, the governments have signed up, and bear this in mind in terms of future priorities and directions of travel. And I just highlight this particular couple of paragraphs on global monitoring of OA. The importance of emerging technology and sensor development is pulled out here, and the need also for cross-sectoral partnership between government, industry, and academia to facilitate, a true global monitoring program. I'll come back to that at the end of the talk. The work that we're going to discuss today has actually allowed us now to, at the university, conduct the analysis for both Scottish and Irish governments in terms of long-term ocean acidification monitoring. So that analysis is currently done in Edinburgh in the Changing Oceans Lab, and we connect in nicely to the Northeast Atlantic GOA-ON hub in terms of where this work is carried out. But we don't restrict our activities to the Atlantic. We've actually started a pilot study in the South Pacific. One of the largest marine protected areas is around the Pitcairn archipelago, and with very low cost approaches working from rubber boats, we've run the first series of samples down to 200 meters to provide a baseline. I actually presented this to the Foreign Office in London just yesterday. And I think one of the take-homes from our presentation today is really that we've been able to really bring down the costs of the analysis. And so to scale up and work with citizen scientists and others suddenly becomes feasible. And this is something we're really keen to expand upon. And there's some interesting hints coming out from that work in Pitcairn. There's a health warning on the slide because our CTD data were sadly not from the year we took the samples because the sensor wasn't working. And this is the nature of sometimes working in remote places. But it does seem that both the pH and our calculated aragonite saturation states are a bit lower than the estimates in government reports. So that's something we're keen to follow up on. This is just a one spot measurement. We want to work with the local islanders to actually ramp up our continuous monitoring. So what I'm now going to do is pass the microphone over to Gavin, and Gavin, I will advance the slides when you tell me. Thank you.
Thanks, Murray. So I'll just quickly go through the measurements, how it's done. And traditionally, total alkalinity and dissolved inorganic carbon, there's best practices for these measurements, and these methods have been optimized for seawaters. And generally, the alkalinity is measured using a titration, and dissolved inorganic carbon is by acidifying the sample to drive all the carbonates into carbon dioxide, then measuring that carbon dioxide as it comes off the sample. So if you move on to the next slide, Money. So for ocean acidification measurements, we really need high resolution measurements with low uncertainties and high accuracy. And I've put up these numbers here. 0.2% relative standard deviation and bias is like the benchmark that we've been working towards for the work that we've been doing. If you go on, Murray. So to automate the process, like I say, we need to maintain this high quality data, but also we need to reduce the cost and increase the throughput. And the major way of doing that is really to reduce the labour input to the measurements. To increase the throughput, we could pay technicians to work all the time and get more samples analysed that way, but it's going to become very expensive. So our first thoughts for this year was to, well, why don't we replace the technician with a robot and get a robot to do everything that the technician's doing? So go on, Murray. So the first attempt was a robotic sampler, which was built by our senior mechanical and electronics technician here in the School of Geosciences, Matt. And it basically consisted of a large auto sampler, so we could rack up the samples as they were received in the, I think it was 250 ml bottles here, and then built a robotic titration arm to do the kind of flush night and move the cell. So we don't need anyone to be there to like babysit the analysis all the time. Go on, Matt. So this year worked really well. The labour input for about 37 samples was about 2 hours. And we managed to increase the throughput by able to run the analysis for 16 hours continuously. And that was really just limited to the size of the auto sampler. And crucially, there was no change in the accuracy or reproducibility from running the samples manually compared to this automated process. So worked really well, but like I say, the robot was complicated, needed relatively large sample volumes. We're using about 80 mils of sample, which is fine for the open ocean stuff, but when it came to experimental work, this was really a wee bit too much. Because if you're taking water out of the tank, at some point you're going to end up with nothing left there. And it was relatively slow, 25 minutes per sample, with the alkalinity be the limiting step. So this was the part that we really focused on for the next part in getting the higher throughput. So to do that, if we have a wee think about the alkalinity theory, theoretically, if we were to have the sample and add a known amount of acid to the sample, by measuring the resultant pH, as long as it's below the equivalence point for the titration, which is about pH 4.5, if we measure that final pH very precisely, we can then figure out the alkalinity in the sample by just doing one measurement. The problem with this here is the changes in pH are really too small to be precisely measured using like a conventional benchtop pH probe. So to improve this here, we decided to use colorimetric pH measurements to set up a method so we could do colorimetric alkalinity measurements. And this here can be done using bromophenol blue, which is perfect for this. It works really well between pH 3.5 and pH 4.5, which is just below the equivalence point. Using this dye, we can resolve these small differences in pH that's required for giving us the quality of data that we require. This is not something that we came up with ourselves. The method itself is based on the bromophenol blue method, which was proposed by Nand and Elwood. And because it's a colorimetric method, it can be automated on any auto analyzer, really. And this has been done by others. Scalar have got a method and have been collaborating with the Royal Belgian Institute for National Sciences. I must admit, I haven't actually reached out to them or to see how they get on with the method, but I'm led to believe that they're using it for their ocean acidification measurements. So we were able to put it together in our serial analytical AA3 autoanalyzer. And this is a really common instrument used for nutrient analysis. So it's not a purpose-built instrument necessarily for measuring ocean acidification parameters, but it did mean it's low cost and really high throughput. We're able to measure a sample in about 3 minutes, which made it a faster technique than the inorganic carbon measurements. And the labour input is even less. So we're looking at maybe up to 2 hours of labour to get back up about 100 plus samples, and crucially, really low volume at less than 5 mils per sample. And like I was saying earlier, there's no point in automating anything if the quality of data isn't good enough. So from our measurements, we're getting our typical standard deviations down to about 3 micromoles per kilogram, which is less than the 0.2, like the magic number that we had for the RSD of the samples. And if we compare that to other technologies out there, I know this table up on the screen here is a wee bit out of date. It was produced in 2010, but we're really up there, getting close to the state of the art with the state of the art techniques. But the crucial part of it is really the throughput, because we can put more samples, measure more samples at lower cost. The statistics can be better because we can have more samples, more replicates, rather than wait, because we've reduced the cost and the time taken. So the application of the method, I mean, last year we analysed about 2,000 samples, and the majority of these came from 2 large projects. And we can comfortably analyse up to about 100 samples per day. And like Murray was saying earlier, we've had samples from the Scottish Government and the Irish Marine Institute, and have been running the samples for them. Also, experimental work, we can use lower volumes, faster turnover in results, which means that you can have quicker data, especially if that's going to affect how the direction of your experiment. And it also just means you can have a higher sampling frequency for the experiments as well. So just here's a quick slide to show some of the applications. So here in the University of Edinburgh, in School of Geosciences, in collaboration with the St Abbs Marine Station, multi-factor coral experiment where the aragonite saturation point needed to be measured. And I think in total there's over 500 samples with high frequency measurements. So really able to produce these large data sets really quickly at a low cost. But crucially, the low sample volume means that because there's the infinite volume within those tanks, we can allow for more samples to be taken from the same volume of water in those tanks there. So in summary, we were able to create a method that was high throughput, low cost, but the crucial part here was there was no real compromise on the data quality, and we were able to bash through up to 100 samples per day. And the method has been used for both ocean samples and lab experiments. I think we've measured from the North Sea, Atlantic, and Pacific now. And the reason we were able to do this was by changing from the ground titration to the colorimetric alkalinity measurements. So I'll pass you back to Murray for just a few quick words.
Thanks so much, Gavin. And all I was going to do was just wrap things with a couple of thoughts. I think to upscale what we're all doing, engaging with industry is going to be important. And it brought me back to a pilot study I did 10 years ago, actually with BP and Guardline. And you can see the dots on the map. We sampled from the North Sea, from the Med, and from West Africa, and generated with an old school approach the data you can see just in terms of aragonite saturation state to depth. And I think these partnerships with industry are going to be really important as we upscale what we're all doing. And I'm happy to say we're collaborating with the NOC and their BORA Blue Ocean Research Alliance program. It's a decade program, I understand, Ocean Decade program. They've instrumented some of the Hercules remotely operated vehicles on Subsea 7's ships with a sensor package. I was at sea with that this year, and we took the water samples with Niskin bottles on the ROV to cross-calibrate those sensors with our TA and DIC measurements, as Gavin's been summarizing. Really excited to see how those results develop over time. So just some concluding thoughts. Industry engagement, I think it's going to be key, and because we now can get far more samples through, I think we can start to really upscale. We can drive down the costs, and we're really excited, as with the PitCan example, to share and enhance this approach and to build the capacities across the world. So thank you all very much for listening. These are our extra slides, which we have in reserve. Catherine, I will bring it back to you.
Thank you both so much for that excellent presentation. I'm excited to talk more about it during the Q&A portion. So next, I would like to introduce our following speaker. There we are. I think it's okay, yes, there we are. All right. Perfect. So now I would like to introduce Dr. Simon Whelan and Dr. Simon Ussher. I believe that they are in the same room, so there may only be one of them on the screen at a time. But thank you both for being here. So Dr. Simon Whelan is a research associate in environmental sensors at the University of Plymouth. His research interests include the development of electrochemical sensors and field effect transistors for environmental, biological, and medical applications. Dr. Simon Ussher is an associate professor of marine and analytical chemistry at Plymouth University School of Geography, Earth, and Environmental Sciences. His research interests include trace metal biogeochemistry, coupling biogeochemical models with physical and ecological models, shipboard analytical methods, and trace metal and nutrient sample processing and analysis. So without further ado.
Hello, can you hear me all right? Oh, wonderful. Okay, is my screen being shared? No, okay. Now it is. No. Now it's okay. Okay, cool, wonderful. Right, okay, I'm Simon Whelan, and yeah, so I'm here to talk about the work we've been doing at the University of Plymouth to develop a large sensor network to monitor changes in ocean pH. So the main point of this project is that we want the sensor to be low cost as well as mass producible, because we really want to get a wide view of what's going on in the marine environment. So at the moment, there are a few different sensor networks that have been deployed. I think the most substantial is probably the Argo floats, which measure temperature as well as various other environmental variables. 453 of them are capable of measuring the pH of the ocean. So there's room for a lot more sensors, because the ocean is obviously a vast place, and ocean pH is not constant in any, throughout different places. Like for example, coastal pH is more subject to variation due to like localized pollution and that sort of thing. So this is a slide showing you the Argo floats network. It does cover quite a lot, and but not all of those, as you can see underneath there, not all of those floats are capable of measuring the pH of the ocean. So we do need to have more sensors. In addition to that, there are things like gliders and automated boats and submarines, and you can also attach pH measuring facilities to cruise ships and merchant vessels to sort of get more and more data. So to date, there's been quite a few attempts at making sensors for this sort of thing, but none of them have really been deployed in a mass, a huge manner like what we're aiming to do. And what we want to do is make sensors that are very, very cheap as well as effective, to give like a higher resolution of changes in ocean pH. So the approach I'm going to talk about today is the electrochemical approach. So these sensors that we've created are electrochemical, and there were two two pH-sensitive materials were tested, and these are graphene oxide and DMSO-melanin. And these are materials that are known to change in response to pH. And so we've used screen-printed electrodes. Screen printing is a very old technique that's used for sort of transferring art. So you transfer a design onto a substrate by coating this the mesh with ink and then just passing a squeegee across it. So that's how we've created them. And screen-printed electrodes, basically, there's 3 electrode system that consist of a working electrode, a reference electrode, and a counter electrode. And what we're doing here was modifying the working electrode to confer pH sensitivity by applying a layer of either DMSO-melanin or graphene oxide. This is called drop casting. And this is an example of the various stages of building up the screen-printed electrode. So on the far left there, you've got 3 tracks of conductive silver ink that also comprises the reference electrode at the top there. And then there's a layer of conductive carbon, which is a mixture really of basic graphitic flakes and carbon black. And that sort of produces the working and the counter electrode. And then on top of that, there's a protective layer of dielectric ink that insulates the tracks. And these are, I have made them before myself, but for what we're doing here, we're buying them in from Zimmer and Peacock ready-made. They're high-quality sensors, very cheap, about 99 cents per sensor. So that's the kind of price that you need for a mass-producible network. And these are just the 2 molecules that we're using here. So we've got DMSO-melanin there on the right, and graphene oxide on the left. And this is a cross-section of the screen-printed electrode. One of the DMSO-melanin is the example. You can see the very thin red layer on the top of the working electrode represents the DMSO-melanin. So now on to some results. So first of all, to show that the sensors they're not inherently pH sensitive. This is a non-functionalized sensor, so there's no melanin or graphene oxide applied to the working electrode, and you can see there's no pH sensitivity whatsoever there. But applying either the DMSO-melanin on the right or the graphene oxide on the left, you can see there's a pH sensitivity they do work. They start to work and become pH sensitive, with the melanin showing to be significantly better than the graphene oxide in terms of it's both higher in sensitivity and there's less error. But this is just in reference buffers. Reference buffers are fine, but the problem with the reference buffers is they present an idealized sort of conditions. So it's also we also tested them using artificial seawater using this formulation to sort of see whether the various components in there sort of may interfere with the sensors, because sensors are sometimes subject to like sort of interference and variation. And they completely wipe out the graphene oxide sensors. They don't work at all in artificial seawater. But the melanin sensors, they're still showing some sensitivity, although it's not as high as it was in reference buffer, but it's still pretty good. And it's still got a clear distinction between these levels here. So we've got pH 4, 7, and 10. But they're not really very environmentally relevant levels. They just show that the sensor is pH sensitive. So in addition to that, there's also tested applying just modifying the pH slightly over a much more narrow range that's more useful for monitoring the sort of changes that we see in the ocean. And you can see that they do respond across this narrow range as well, which suggests there might be some real world applications there. Furthermore, sensitivity is not enough alone, because if they die too quickly, then they're not very good for a network. So looking into stability. So for this test here, sensor was immersed in the artificial seawater over 2 months. You can see the melanin there, because I didn't take graphene oxide forward any further because it didn't work. So we continued with the melanin. And yeah, it appears from the photographs there, so initial on the A is basically time 0, B is 1 month, C is 2 months, and they seem like it's holding up pretty well. But so then I tested again for pH sensitivity after the 2 months, and we're still seeing pH sensitivity there, although the signal's a little bit more wavy than it was. So I think we do need to look into sort of developing sort of protective housing. And there is work underway to do that, but that's quite new, so it's not made it into this presentation yet. So yes, future work is basically stability is the big thing. They work. They are able to measure changes in well, certainly in the artificial seawater, and to test real seawater and test long-term stability and create some protective housing. That's what we need to do next. And that is it. Is there anything you want to say, Simon? No.
Great. Thank you so much to both the Simons there. Thank you for the presentation. All right, I will go ahead and introduce our next speaker. So there we are. I would like to introduce Reggie Spaulding. Reggie is a senior scientist at Sunburst Sensors, a microbusiness of around 8 employees. She has a PhD in environmental chemistry from UC Davis and has been developing and testing instruments that autonomously measure carbon dioxide, pH, and alkalinity in the ocean for over 20 years. All right, Reggie, take it away. We can see your screen, but we cannot hear you right now.
How's that?
Yes, that's great.
Okay. All right. And you see the presentation now?
Yes, I can see the presentation.
Okay. All right. So I'm going to talk about 2 instruments that we've been developing called the MOBI-pH and the MOBI-alk, which are small handheld instruments used for measuring pH and alkalinity. And thanks to the speakers before me, I don't really have to cover much of this, but just to say that carbon dioxide in the air equilibrates with carbon dioxide in the ocean and produces carbonic acid that dissociates to bicarbonate and carbonate ions, as well as hydrogen ions, decreasing the pH of the ocean. And 2 ways that we can describe that are by measuring the pH, which is the negative log of hydrogen ions, or the total alkalinity, which is the sum of the alkaline ions minus the acidic ions. So almost all of our instruments at Sunburst work off the principle of colorimetry, which has also been covered a bit. We use sulfonophthalate indicators, which have a color change with pH. So what I've shown down below is metacresol purple, which is commonly used for pH measurements. It has 3 forms. At pH 1, it's bright pink. At pH 4, it's yellow. And at pH 10, it is purple. And we only focus on the what I'm calling the HI minus form, which is this one, which has lost a proton at the sulfonyl group, and the I2 minus form, which has lost a proton at the another proton at the hydroxyl group. So this is what the absorption spectra of those 2 forms of the indicator look like. So at pH 5 or a low pH, the solution is yellow and the maximum absorbance is at 434 nanometers. At pH 10, the solution is purple and the maximum absorbance is 578 nanometers. So we can use these unique absorbances to calculate pH using a modified form of the Henderson-Hasselbalch equation shown here. And you just need to know the pKa of the dissociation of the indicator. And you need to know the absorbance at these 2 wavelengths. And this R represents the ratio of that absorbance. And then these E's are just constants in the equation. So when you're using colorimetry, there are many sulfonophthalate indicators that you can choose from. And what you're looking for is something that has a pKa right around the pH of whatever you want to measure. So we can measure pretty accurately pH at plus or minus the pKa of the indicator. And the pKa of the indicator is going to be dependent on both salinity and temperature. And I highlight here metacresal purple, which at salinity 35 and 25 degrees Celsius has a pKa around 8. So that one is perfect for measuring pH in the ocean. I'm also highlighting bromocresal green, which has a pKa of 4.4 at salinity 35. And for doing alkalinity titration, since you're adding acid and bringing the pH down, this turns out to be a very good indicator for that. This slide shows the bromocresal green, which we use for the alkalinity titrations. We use exactly the same principle as we do for pH measurements, where we're measuring the two forms of the indicator, one that absorbs at 442 nanometers. This is shown at pH 2.6. And then at pH 4.7, predominantly we have the basic form of the indicator, which absorbs at 616 nanometers. Now, when we do these titrations, I think one of the speakers already talked about this single-step acid addition that was published by NAND. And we combine that with the titrant monitored titration, which was published by Martz. And so that means that we mix the indicator and the acid together, and we add that all in one big addition to the seawater and bring the pH down. And then we measure the pH exactly the same way we do for with metacresal purple, only at different wavelengths. And down below, I'm showing how the titration of, oh, my slides always do this, take too long on this slide. This is showing the titration of the carbonate species in the ocean. So the endpoint is here at around pH 4.3, where bicarbonate ions are equal to hydrogen ions in concentration. We bring the pH down to about 3.5 when we do this single step. And what that does is that allows all of the carbonate to turn to carbonic acid and then off gases, CO2. And then in that case, your total alkalinity is dependent on the minor species in the solution, which are the sulfate ions, hydrogen fluoride, the indicator, and hydrogen ion. And then rather than measuring a precise volume, we're measuring the concentration of the indicator, which we can calculate back to the concentration of the indicator in our solution that we added to the seawater. And that tells us a dilution factor. So the design of our instrument, the MOBI, looks like this. It has 3 machine parts that snap together, 5 small electronic boards that snap onto that. And then there's a glass vial, which is used as the spectrophotometric cell, and then an off-the-shelf case that this goes into. This is what it looks like when it's all put together. On the bottom of the unit, there's a power button as well as a USB-C charging port. Inside of the MOBI, there's the glass cuvette, and we have LEDs that shine on one side of the cuvette and then a photodiode on the other side, a thermistor on the bottom to measure the temperature. The wavelength of these LEDs will be dependent on which indicator we're using. This is shown for 434 and 578 for metacresal purple, which is used for pH measurements. So what we do is you add seawater to this cuvette, you shine the light through the solution and detect the intensity with the photodiode, and that is the I0 in this absorbance equation. And then you add reagent, mix it up, and again, shine the lights through the cuvette, measure the light at the photodiode, and that's the I in the absorbance equation. So that's how we get the absorbance. The MOBI can be operated with either a smartphone app or a web-based app. I'm showing the smartphone app at the top and the web-based app at the bottom. They both have the same functionality. You basically open up your app, you choose your instrument, connect to it, and then you add your seawater. you press the measure blank button on the app, and then you add your reagent, you mix it up, and you press the measure pH. Now this is shown for pH. It's basically the same thing for alkalinity measurements. And then there's a sharing function here so that when you're finished, you can see it gives you a pH and a temperature and the salinity, which you've actually entered. But then you can share it via whatever sharing function you like to use in it. You get a CSV file, which has a lot more information in it than what's on the screen. So I'm going to show a little bit of data here that's been collected with the MOBI. This is, in this case, we used 2 different MOBI units. We measured tris buffers that were prepared at 3 different pHs. And then we measured all of them at 3 different temperatures, and there were 5 replicates of each. So each point on this graph shows is a representation of 5 measurements. On the x-axis is temperature, and on the y-axis is the pH offset. That is the pH that was measured by the MOBI minus the pH that we know the solution should be. And overall, the accuracy was 0.01 plus or minus 0.007. And I compare this to a YSI pH probe, which is commonly used for handheld, measurements. And some of our collaborators have worked with us to look at the accuracy compared to the MOBIs, and the accuracy of the YSI can be off as far as 0.3 pH. So next I'm showing some accuracy using the MOBI-alk. And here we've used 5 units, and all of these measurements were taken at room temperature. There were 4 different seawater samples, each which had a different alkalinity. And we did, again, 5 replicates for each instrument. So again, each point represents 5 measurements. On the bottom, or on the x-axis, is the known alkalinity, and on the y-axis is the alkalinity measured by the MOBI minus the known alkalinity. And you can see that up in the left-hand graph that our accuracy was off by as far as 250 micromoles per kilogram. So then what I did is I took one of the points, one of the seawater samples, and I used that as a standard, and I did a single point calibration, and I applied the calibration factor to the other measurements, and that brings down the accuracy to 13 plus or minus 34 micromoles per kilogram. I compare that to the HANA handheld colorimeter, which is used for aquariums. And this one, even when I applied a calibration factor, the accuracy was minus 163, and poor precision as well. I am going to skip this slide out of time. And then I just wanted to show some data that has been collected by some citizen scientists in the Monterey Bay area in California. They have been collecting pH measurements, first with what we used to call the fighter, and that's shown in orange on the bottom graph. And now we've changed the name to the MOBI, and that's shown in blue. They've been collecting weekly pH on the Santa Cruz Wharf for almost 3 years. And so this is a time series from that. They're also starting to use the MOBI-alk, which is shown in the upper right corner. And those measurements, they've done replicates at several different times. And I'm going to move on to some other citizen scientists who have collected data using the MOBI-pH on the northeast coast of the US. And they collected samples at 3 different sites on 3 different days. And they also collected bottle samples and took them back to their lab and did spectrophotometric pH. So when we're looking at a circle here, that's a MOBI-pH, and the same colored square is spectrophotometric pH of the same sample. And the average difference between the MOBI and the spec pH was 0.02 plus or minus 0.03. And I see that I'm out of time. I just want to briefly mention that we have a map app and database app that we will be launching very soon. That you can, when we get the functionality on our phone app, you'll be able to push the data to this app, and you'll be able to visualize your data here, as well as other people's data that they've collected using the instruments. And I just want to thank my collaborators on this, the citizen scientists involved from the University of New Hampshire, Cabrillo College, Friends of Casco Bay, and Wells Reserve. And thank you very much. I'll stop my sharing.
Thank you, Reggie. Thank you for that great presentation. And hopefully we could talk more about the upcoming website function during the Q&A.
Sure.
Thank you again. And to introduce our last speaker, last but not least, I would like you all to meet Anthony J. Lucio. Anthony is an early career ocean professional with a PhD in chemistry. He is a senior research engineer at the National Oceanography Center, where he develops sensor technology for measuring the ocean carbonate system. He also leads development at the National Oceanography Center into electrochemical sensors to study biogeochemical processes. Thank you, Anthony.
Thank you, Catherine. I'm just gonna get my slides up. Make sure that works okay. Share that one. Can you guys see that okay?
Yes, we can see them.
Okay, great. Yeah, thank you. Awesome. Well, yeah, thanks for that introduction, Catherine. It's great to be here during Ocean Acidification Week, especially within the technology session. And I'm super excited to tell you guys about some work that I carried out last summer, which was a 6-month deployment looking at a range of different pH sensing technologies and how we might actually combine them to get both accurate and rapid sensing of seawater pH. So why do we need accurate and rapid pH measurements? Well, I don't think I need to labor the point to this group, but we, just so you're aware, the pH of our oceans are changing on the order of about 1 to 2 milli-pH units per year. And while that might seem small, the pH of our oceans is a fundamental component that not only impacts, but is impacted by a range of different processes, talking about things such as like calcifying organisms, how ocean acidification can impact wider ecosystem functioning, ranging from species small to big, and also as we, as a community, move toward climate change mitigation strategies such as carbon capture and storage and carbon dioxide removal. And it's fantastic that this body, GOA-ON, actually produced some guidelines a while back looking at recommending climate quality uncertainty goal is letting us know that we actually need to have an uncertainty of about 3 milli-pH units. So that's just kind of the target we need to aim for the sensing technology that we develop to be able to reach. So what kind of sensors do the oceanographic community currently have? I think far and away the most widespread marine-based pH sensor is an electrochemical-based measurement. And this is just an ISFET example here, which is a sensor from Seabird. This is in their CFOX kind of form. We actually deployed this in our study as well. And just for reference, the CFET, which is the pH sensing side here on the left, and then directly attached to it, you can see they've got this CTD to provide the salinity, temperature, and depth data, which feed in and impact the pH. This kind of sensor, the CFET, basically has been proven over decades. It's very accurate. It's got a great resolution and a very fast sample frequency. However, it is quite costly. I think the community will be, I think, aware of that, and they can often come with long lead and service times, which for the community isn't a good thing. So having more options is definitely a good thing. So I'm from the National Oceanography Center, and over the past decade, we've kind of pioneered this lab-on-chip technology in the marine community across a range of different chemistries. In today's talk, I'm just going to refer to the pH sensing that we've done, which is based on a spectrophotometric measurement. These sensors as well, they're quite accurate. They've got great resolution, and that is afforded by having some onboard reagents as well. The sample frequency isn't as fast, so here we're on the order of about every 10 minutes to be able to get a sample out. And just for reference, for the ISFET, you can sample on the order of seconds. However, where the lab-on-chip technology has been known to suffer is that they can be quite power hungry. So power management during a deployment is definitely a key consideration to bear in mind. And lastly, a relatively new entrant to the market is actually these optode-based technologies, which I've got a picture here from Pyroscience, which is just one of their pH Aquafox loggers. And I do want to point out these pictures are not to scale. These are just kind of stock images that I've gathered from the web, but it's based on a fluorometric-based measurement. These sensors, physically, they're quite small. It's got a rechargeable onboard battery that I've tested, and it does last what it says on the tin, which is fantastic. They can sample very fast, but most importantly, I think the cost of these is fantastic. They are very inexpensive sensors to get your hands on in comparison to some of the other sensors that I've deployed during the study. However, where they do suffer is in their accuracy and signal drift, as we'll see with some of the data that I'll show you. And the kind of point of the study that I want to show you is, can we actually combine two of these technologies where you may have something that samples less frequent, but you know is accurate, and couple that with something that, while it's not as accurate, you can actually sample very, very fast. And that's actually what we've done throughout a 6-month deployment. Just outside the NOC's quayside pontoon, I deployed a range of different sensors, I think 7 in total, but I'm just showing you a selection of them here today. And this is kind of a global snapshot of the 6-month data set. We've got depth data, we've got temperature and salinity, but the cream of the crop is the pH data that I've got down here. And you'll notice I've got 2 pairs. I've physically attached 2 optodes to 2 lab-on-chip sensors, as indicated here on the left, and I've got data over the 6-month period. And discrete co-sample data, which is like just me going out with a syringe manually sampling some seawater, bringing that back in the lab. That's the discrete co-samples sprinkled in these plots as the yellow dot. So that for us represents the true seawater pH. And while we did run into some power management issues along the 6-month period, far and away, I think the largest thing for us was the biofouling that we incurred. So this was deployed at a fixed depth of 0.5 meter below the sea surface. And you can see from day 0 to day 30, we had a chaotic mess of bioaccumulation all over the sensors. So just trying to illustrate the challenging environment that we put these in. However, over that 6-month duration, for the 2 lab-on-chips that I deployed, their accuracies were on the order of about 14 to 19 milli-pH units with respect to those discrete co-samples. And you can see those data compared with the black and the red dotted traces and how that overlays with the yellow dots as well for our discrete co-samples over that 6-month duration. The other 2 traces, the light blue and the light orange, you can see those are our optode data sets, and we'll talk a bit more about those in depth, but you can kind of see there's some interesting things to talk about as we continue. But as I mentioned, this is just a quick 6-month snapshot of it, but if we actually zoom in on like a day or 2 set of data, you can kind of get an indication of, in this instance, how we can see some nice tidal variation happening and how those tide changes impact the salinity that we get out, and then how that salinity then itself impacts the pH that we read out. One thing I do want to point out with this plot as well, it should be apparent, but I do have 2 vastly different sampling frequencies for the lab-on-chip versus the optode data. So the lab-on-chip with the black and red dots was sampling about once an hour, versus the optode was sampling once every 30 seconds. So just world difference in what you can actually achieve with the optode technology, which is fantastic. So you really do capture that feature-rich pH data, which is great. But as I mentioned previously, you can see the data itself here is a bit offset from not only the lab-on-chip, but also our discrete co-sample data. So we wanted to actually look at how we could correct this data. So I've just put together a really simple kind of cartoon schematic to illustrate how we're actually approaching this data correction, because it's a post-data correction that's applied after the deployment's done at the moment. So if this gray line here just represents our true seawater pH, basically what we've seen from our study is, while a lab-on-chip doesn't sample as fast, when it does sample, it is very accurate, which is great. So you can kind of get a response like this. With the optodes, however, we can sample at a much faster rate, but you'll notice we've got the right curvature in most cases, but in this instance, I'm trying to illustrate the data being offset on the Y scale. So we've got the wrong pH values coming out. Or, as you probably saw from that quick snapshot, we could also have situations that might look like this, where again, we've got the right curvature, but it just seems to be drifting toward further and further pH values away from what we know it to actually be. So the idea behind this linear rate correction is if we actually just sample 2 lab-on-chip points, and here I'm just trying to indicate if you take a sample at the start of the day and at the end of the day, so just a single point measurement once a day, and do a best fit line to that, and then apply that linear regression to the optode data, whether that be a signal drift or an offset optode data set, you can actually correct it to get data that agrees much better with the discrete co-sample data, which is ultimately what we're aiming to do. So now if we revisit that optode data set, here it is in its raw form, just in comparison to the discrete co-sample data. So sorry if the slide's a bit slow. There's like 250,000 data points in that blue trace alone. But yeah, what we can see is there's two phases really to this, which is kind of indicated by this very stark break in the curve, which was phase 1, phase 2, just the first 3 months, second 3 months. You can see within the first month and a half, we had pretty reasonable performance, but then thereafter we saw significant signal drift. And I do want to point out, my colleague and I intentionally let this happen to test the limits of this sensor. And we can start to, kind of postulate what that signal drift may be a result of. I think we can definitely demonstrate we had a lot of bioaccumulation occurring, but also because of our high measurement frequency, we might be photooxidizing that polymer film that's actually doing that pH sensitive measurement. And just as a quick indication, halfway through the study, we actually had to replace the optode because this is what it looked like at the beginning. But around peak biofouling, you can kind of see what the inside of that polymer film, that optode, looked like. And effectively, halfway through, we removed the sensor from its site, cleaned it up, put a brand new pH optode cap, and those caps are meant to be considered a consumable, so you can just put a fresh one on, recalibrate, redeploy, and that's ultimately what we did. And you can kind of see the curve on the second half of this brought that curve right back down, but we're still seeing an offset of about 100 milli-pH units, even in phase 2. But now when we think about applying that correction method that I just outlined, the dark blue trace is taking a lab-on-chip sample once a day and applying that linear regression onto the optode. And you can see we get a much better agreement between the corrected optode data and our discrete co-sample data, which is fantastic. And in this instance, we were able to drop the accuracy to rival that of our lab-on-chip itself, which was used to correct it, which is really, really neat. But now if we actually, again, this is just a global snapshot of the 6-month data set. If we actually zoom in and look at kind of 3 different regions, kind of toward the beginning, the middle, and the end, here I've zoomed in on just like a 24-hour snapshot. And I've got overlaid in the dark maroon or brown color. This is that seabird sea fox, which is labeled as the ISFET sensor, which also sampled quite fast as well. Just to demonstrate at the beginning, we are getting not only the feature-rich data from both sensors, but they agree, and they also agree with the co-sample data, which is fantastic. And I think most importantly, this point here in the middle, I just want to remind everyone, this is happening with, again, very unrealistic pH values that we're reading out from the optode. But what's fantastic is, although we're getting unreasonable values, when we do correct it with this very simple once-a-day lab-on-chip correction method, not only do we get those features coming out, but we get good agreement with the independent pH sensor that we deployed, in addition to matching up reasonably well with our co-sample. And just to iterate that again, bringing it back home toward the end of that 6-month deployment, we can just see that, again, the curves are still lining up quite well between them. And you'll notice the number density is decreased here because in phase 2, we dropped the sample frequency to kind of get an indication if that was impacting the data overall. But I don't think we really saw that bear out from what we found. So yeah, if I could just end there with just a couple of recommendations for the community. And this is actually something we're putting together in a manuscript that we're hoping to submit hopefully soon, is really, I hope I've demonstrated that by combining lab-on-chip and optode technologies, you can really have complementary strengths where you've got accurate and rapid sensing capabilities. And a simple linear offset adjustment, actually once a day or even every 3 days, is actually sufficient to provide accurate optode pH data. And to kind of graphically demonstrate that, I've plotted on the y-axis here the accuracy of the optode as a function of power required to achieve that accuracy. And by power required to achieve that, I'm actually implying how fast we're actually sampling the lab-on-chip. So just as an example, this point here is sampling once a month with that lab-on-chip. You can see the accuracy is quite poor, but we don't need that much power to do that. On the flip side of that, if we go sampling that lab-on-chip once an hour, we get fantastic accuracy, but obviously that's going to require a lot of power. And what we found is roughly every 1, 2, and 3 days is actually sufficient to give you an accuracy with what you'd get when you sample almost as fast as we did for this particular deployment. over 6 months, and it doesn't really require that much power. And just as a reference, a simple marine-based commercial battery that can be deployed at depth can easily achieve power requirements up to here. So we're not really asking it for too much when we drop it down to 1, 2, or even 3 day kind of measurements. And I think the point behind this is really that the correction interval can be dialed basically depending on the power requirements for that user's deployment, with a very known and quantifiable impact on its accuracy. And I think the last point I want to say, because obviously we're deploying 2 sensors in place of 1, but which sounds a bit redundant, but I think for the for my experience with just over the course of 6 months, things going wrong, deploying two independent sensors actually can give you a greater chance of success, especially when you're doing something over a very long period of time, or in remote locations where you might not be able to check on how that sensor is performing, or even perform any kind of like maintenance or upkeep on the sensor. And with that, I'd just like to thank the funders for this work. The first one, Project Greensand, which is an EU-funded project that really got this work undergoing for me. And also the NERC-funded Atlantis project as well, which is carrying this work on for me now. And lastly, I just wanted to thank a few collaborators and also Power Science for lending me one of their optodes for testing in this study as well, which was great. And with that, I'll end it and take any questions.
Great, thank you. Thank you for the great presentation. And thank you to all of our speakers for presenting your work so effectively in such a succinct amount of time. I know that that is no easy feat. So hopefully we can dive a bit more into the details now as we start the Q&A portion of this session. I think there are a couple of questions in the Q&A box. Maybe we'll take the one from Simon Ussher first, because it's for you, Anthony. So while it's fresh on the brain. Simon, I don't know if you would like to ask the question over the screen, or I can read it from the chat if you prefer. Also, it looks like we still are sharing a screen if we want to end the screen share.
Okay. Can you hear me okay?
Yes.
Hi, yeah, really enjoyed that last talk, and thanks so much for that, and really important work to do those intercomparisons. I was just interested genuinely on this. You meant you've been using the term accuracy at the end. Just wondered how you define that, because obviously there's different ways of doing that. So yeah, just interested. Thanks.
No, that's a fabulous question. Thank you for that. In this instance, I'm defining the accuracy of those sensors always in comparison to the discrete co-sample, which was collected at the same not only water mass depth, but also the same point in time when those sensors were sampled. However, I do have to admit, over the course of a 6-month deployment, timing 7 different sensors, I did have to have a wee bit of wiggle room in what I call the same time. So roughly, I think it had to be sensor dependent on when that was done. But with respect to the original question, yeah, it was always with respect to that discrete co-sample data that accuracy is quantified against.
Sorry, can you hear me again? Sorry. Technology
Yes.
problem over here. Yeah, so I was just wondering, what was the method that you measured the pH when you brought those discrete samples back? That was kind of related to that. That's okay.
Oh yeah, no, sorry, yeah, absolutely. So those discrete samples were collected and then immediately taken into the lab and measured on a UV-vis spectrometer, just with MCP, like bog standard normally would be done.
Okay, right. Thank you.
Cool.
Great, thank you. And then Reggie, I believe you are raising your hand. Is there something you'd like to add?
I just wanted to ask a question to Gavin about the spectrophotometric alkalinity method. And I'm wondering if you have to vary the amount of acid that you add, depending on the alkalinity of the sample, or if there's a specific range of your sample that your standard addition can measure accurately, or how does that affect the measurement?
No, thanks for the question. the method we've set up, we are creating a calibration curve using samples of known alkalinity, and then using the reference material to correct any deviation, small deviation in the calibration curve. So no, we're using the same concentration of acid that's been added to each sample, but then because we've got a calibration curve for each session that we were measuring, that there's the reference for the measurement. And because it's such a quick, cheap analysis, we're able to put in lots of reference materials throughout the run. So generally every 10 samples we'll put in a CRM, and then that takes into account any drift or anything like that, and we can correct the data afterwards.
Gotcha. Thank you.
Thank you. And then Reggie, I believe we have a question for you. I'm not sure if Nuria would like to say that question aloud. Otherwise, I will read it from the chat. Give just a moment to see if they would like to speak. All right, I'll read it from the chat. So the comment is, hello, my name is Nuria Tecido. I have a question for Reggie. Thank you for your talk. It was great to know about the MOBI products. Do you know when they're going to be available and at what depth? Also, just a general comment for the session was that they want to say thanks a lot. From the scientific community, there's a need of low cost and high resolution pH sensors.
Yeah, hi, Nuria. Thanks for the question. The answer is that the MOBI is available now, but it is not an autonomous sensor. So it's a handheld sensor that you physically have to add the sample to and push the buttons on your smartphone to get your results. So it's something, that is really made more for a citizen science group that goes out and does monitoring once a week or daily or something like that. It's not meant for deployment. Thank you.
Great, thank you. All righty, and then, yes, we just received a thank you message in the chat. Great, thank you. And then, yes, if any of the attendees have any questions, please either just raise your hand and I will unmute you, or we can answer it in the chat. Just while we're waiting for some of those to come in, I had a question. So one of you had mentioned earlier, in one of the earlier presentations, you had discussed the importance of collaborating with industry and policymakers and also citizen science. And I'm sure we have researchers in the audience who are looking to make similar impacts in their respective field. And I was wondering, for each of your respective technologies, how you collaborate with either researchers, policymakers, or industries to make sure that your technology is having the greatest impact that it can. So I'm not sure who would like to start. Maybe I'll put you on the spot and say Simon. Perhaps not. Gavin, how about you?
So for us, Maury has really been doing the legwork. He's got the contacts with the governments and that, and it was through them that we really got started. We were approached with a large amount of samples that needed analysed, and that kind of took it off. But now that we've got the technology up and running, it's just working with the researchers within our university to start off with the governments that have got samples for us. But we're really at the infancy here, so we're more than happy to collaborate with people. But it's really just trying to get the technology grounded first before we go out there.
Makes total sense. Simon, I'm not sure if you'd like to answer that question next.
Sure. Yeah, I think Simon has put me in the hot seat, so I'll come back for that one. It was So the project we're working on, we're looking to sort of collaborate with other sort of sensor companies. So we have a collaborator over in Austria, Silicon Austria, and we have also been trying to make sure that because obviously we're at an early phase of development here in terms of what we're doing. So we're also making sure that we're collaborating within local marine labs and also with those who are operating autonomous vehicles as well to kind of try and preempt the problems that or as I said, the challenges of doing these kind of measurements. So yeah.
Yes, thank you.
Also we have some collaboration with IBM as well from that side for the data gathering side, which again is trying to preempt how these things might integrate in the future.
Yeah, it's incredible the amount of people and work that goes into these technologies and these projects. So it's great to see. Reggie, would you also like to answer this question? Maybe you could talk about the citizen science and the website that you had brought up.
Sure. Yeah, so we actually received a grant from NOAA, an SBIR grant to work on this project, which really makes it possible because being the low cost instrument that it is, it really is not profitable from an economic perspective. And especially all of the development time that goes into it. I just want to mention that, and that the biggest problem that we've had with this is that we are constantly having to redesign things because, the processor chip is no longer available and we have to redesign the board. Or right now what we're running into is the platform that we're using to program the app is going away. So reprogramming and that all, as takes a lot of effort and time. So that's been difficult, but because of this grant that we've had the money to do these things, and we've had the money that we can actually make the instruments and give them away. So I've been just reaching out to citizen science groups and different people that I know who teach this kind of thing at the junior college and even high school level. And we've been, if they want to collaborate with us and help us test it, we've just been giving it away. And then, the word kind of spreads, I think, when they start using it. But that's kind of how we've been collaborating. And the map, yeah, I'm hoping that we can get this, but this is a software issue where we're having problems with the redeveloping the iPhone app or the smartphone app, but the website is ready to go, and it is a complete map and a database that will store all of the data. And I think on my slide that I showed, you could see little green dots that were fake data that we had put in. But there will be dots all over the map wherever there's, has been data collected. And if you click on one of those dots, it will bring up the data, and then you'll be able to download the data as well. And you'll be able to choose on your phone whether you want to upload the data or not upload the data. Our data all comes with a timestamp and geolocation. So we're not wanting people, if they're doing work in their lab, we're not wanting them to upload that data to the map because we don't want to know where that is on our map, obviously.
Right. That makes sense. Anthony, do you also want to answer this question, or you talked about it a bit in your presentation?
Yeah, no, I just thought I'd just mention as well, it's one of those things, having collaborations with industries vital to help get this technology that we're all developing out there into the real world. And it's at the NOC in particular, I work within the Ocean Technology and Engineering group. So we have staff that range anywhere from people designing the circuitry that go in to run the software and run the mechanical bits, with engineers, and from chemists that are putting together chemical assays that actually do the chemistry that we're sensing. And it's fantastic to kind of see all that kind of come together in one group. And we also at the NOC have an arm, NOC-I, which is basically there to help take the technologies that the NOC scientists are developing and actually getting that out. So yeah, that's a key thing for us as well, is getting those sensors out. And the lab on chip ones that I did mention, the NOC have been working on that for, I think, more than a decade, and we have commercialized some of those chemistries. The pH in particular is a commercial offering through Clearwater Sensors, but But yeah, no, it's vital to get that technology out there, and not only getting it out there, but making it cost effective is a whole nother game as well. Um, so I'm very interested in the work that you presented, Reggie, on the Sunburst stuff, because that's wicked cool.
Absolutely. Thank you. We do have another question in the chat. I'm not sure if Andrew would like to say this question aloud. I'll give you the option to unmute right now if you would like. All right, I will go ahead and read it. It says, as pointed out earlier, there is some ambiguity between the terms accuracy, precision, and uncertainty. How should these best be obtained for the types of sensors described here?
I go ahead, Simon.
Go ahead, Simon. Thank you.
Oh no, I can wait. You go.
I mean, I was just going to say that it all stems back to the measurement of the Tris buffers, which are our standard solutions, right? That everybody should be using to define what is accurate pH for ocean measurements. So that's anything that I present. That's what I am looking at, is knowing what my Tris accuracy is, and then measuring my accuracy based on that.
Yeah, I'd like to mention comment on that as well, because I did report accuracies for those different sensors that we had. And I did mention as well that those were always with respect to the discrete co-sample that was measured in a lab as a lab validated sample. But even the lab measurement itself, I've quantified my uncertainty over the 6-month study. And even with the bog standard MCP with a UV-vis spectrometer, I still had an uncertainty of about 5 milli-pH in the lab measurement alone, and that uncertainty needs to be brought onto the uncertainty of the sensors that I'm using to reference back to. So yeah, I think that's a very important question for how we actually define what that uncertainty is. But I think another issue is we may also understandably use uncertainty and accuracy and even precision kind of as synonyms of one another. So yeah, I think maybe just a bit better of a definition of how those apply to us, our community would be good.
Absolutely. Simon, do you want to add to that as well?
Only to say that I was also interested in that too. So that's kind of answered my question. Thank you. And I'd be because we're kind of new to doing this, and because Simon's developing a material at very early stages. So to find out how to benchmark it against something that everyone else is using is really useful. Thank you.
Great. Gavin, do you want to add anything? Not to put you on the spot.
For us, it was slightly easier because we're using almost like established technologies or variations in that. So for us, accuracy is always referred back to the, I suppose, the Dixon standard, the standard that everyone uses throughout the world. And especially for our alkalinity method, because it's such a fast, easy measurement, we run everything in triplicate, and same with the DIC. So we're getting the, I suppose, measurement uncertainty on the sample there. So everything's measured in triplicate essentially, and the uncertainty or the standard deviation is reported alongside our the mean of the 3 measurements. So slightly easier for us in the lab.
Yeah, I would just add in that we, for alkalinity measurements, we also are referring back to the CRMs that come from scripts. And we do benchtop titrations of our seawater. But again, there's some precision involved in those benchtop titrations, as well as the benchtop pH measurements, like you said, about 4 or 5 milli-pH for a pH, and probably about 5 micromole per kilogram for the alkalinity. So that should be factored in to, there's some uncertainty in our standard that we're referring to.
Absolutely. Simon, would you like to add something?
Yeah, just so a follow up on that. Tris buffers are used for accuracy, and I guess they're made up in artificial seawater, or is that how
Yeah,
they're done?
tris buffers are made in artificial seawater.
So
And
is there a reference material like a real seawater reference material? Could we use the Scripps sample reference material to test for pH? Sorry,
so those
test
are not
accuracy.
defined for pH. They're
Okay.
defined for alkalinity and DIC. So you could calculate
Okay.
pH for those, but that's not commonly used as a pH reference.
Okay.
The reason the tris one of the reasons that the tris buffers is used is it's a very stable pH. So when it's exposed to
Yeah.
the atmosphere, the pH isn't going to change.
Yeah.
Yeah,
Okay. Thank you.
you bet.
Looks like Andrew maybe had a follow-up comment as well. I'm not sure, Andrew, if you'd like to share with that. Right. Okay. I think all the panelists can see. So if you have any follow-up comments to that, I do want to move on to another question though, just to kind of bring it out to a bigger picture, if that's all right. Are there emerging trends or technologies in this field that you think are going to kind of complement or enhance your solution? Kind of a big question.
Sorry, could you repeat that again, Catherine?
Yes, of course. Yes. So I'm kind of trying to discuss maybe where this kind of technology and ocean acidification research is going in the next 5 years or so. And I'm wondering if you can share if there are any emerging trends that you've noticed or in your field that can complement or enhance your solution that you think will make things easier.
I mean, it's interesting. I think what I've seen over the years is it's really a lot of the same, just trying to refine the same measurements that have, or this building off of previous measurements and trying to make them better.
I think we've here down in Plymouth, we've got these kind of high resolution coastal models, and I think that's been an interesting insight from my side as a biogeochemist anyway, seeing how much variability there is in that coastal zone, and that obviously links to the land, how the land's managed and how the hydrology works around and I think there's a piece in there that's interesting, and that's kind of what we're interested in, I guess, is getting enough resolution to actually be able to observe that spatial variability. In terms of how to do that and what's being to enable that, a lot of that's not been worked out yet, but but yeah, that's kind of our angle, if you like, from our side.
Yes, Anthony.
Yeah, I don't know if I have a explicit answer to that question, but one thing that is, I guess, on my to-do list as well is I've got some funding over the next few years to explore electrochem. I'm an electrochemist by training, and I'm relatively new to the oceanographic community. I was like a benchtop chemist before I came to the NOC, so the entire marine-based science is still new to me. But yeah, I've got a bit of funding to look at how we can start developing small, low-cost electrochemical sensors, not unlike some of the work that has been presented previously. So I was quite interested to actually follow up um, with Simon on some of the stuff that he's doing there because I've got some in particular electrochemical questions. But I'd be curious to see what eChem can provide to the oceanographic community in future. So I think for me, that's an emerging trend that I'm going to be interested to follow.
Absolutely. Thank you. We do have another question in the Q&A. I'm not sure if Naraya, if you would like to say it aloud.
Yeah, hello. Can you hear me?
Yes.
Okay, great. Thank you again for this session. Very interesting. And I need to say that my background is in marine ecology. I work on coastal benthic habitats. And also one of my study sites, they are the natural CO2 vents. These systems know that they release large bubbles of CO2. And for me, it is key, it is fundamental to have high resolutions pH sensors and also to characterize all the seawater chemistry. And that's for me it's basic, no? And that is one of the reasons that I find this session very interesting. And I was going to add, no, Catherine, about your big question that no about the tendency for the next years. And one thing that I think that it's important, it's to have almost real-time data. I think that this is also one very important parameter, or no parameter, sorry, way to go, but not only for 1 meter sensors or pH or temperature sensors, but also along depth. No, I think that for coastal research, this is important, and I think that that this is one key research areas, not to move forward. And thank you again. Thanks.
Thank you. Thank you for that comment. Does anybody want to respond to that? I know we're coming up to time, and so it will need to be a short response, unfortunately.
So that's something that we get requests for a lot. Unfortunately, at the moment, it requires quite a bit of development on the user's end, and I'm kind of pushing the company to move towards making this easier for customers to do, providing some kind of solution for customers so it's not everybody reinventing the wheel every time they want to do this.
Yes, Anthony.
Yeah, I'd just like to point out as well, where we are able to within OTE, we do use commercial off-the-shelf parts, just so that way, just like as Reggie said, we don't have to reinvent the wheel for kinds of components that we might be needing to integrate into our sensors. And yeah, so that's another, I think, key thing to bear in mind. And even making these measurements at depth, like I think the lab-on-chip sensors that I showed previously, we do have those contained within an oil-filled pressure housing, and they can be deployed to full depth, which is great. And they'll standalone log and deploy as needed. But getting back communication from that's a whole nother ballpark. Other than like if you deploy it and you go pick it up, you can get the data, but actually getting it like real time, like on your computer as it's deployed, that's like a whole nother issue outside of my area for like how to communicate with sensors like that. But yeah, I think that would be a key thing to know that your sensor is actually working once it reaches that depth.
Great, great. Thank you all. And thank you for your great presentations and for attending, across continents and time zones. We really appreciate all of the speakers for taking the time to share. Would also like to thank all of the audience members for attending and for participating. And it's been really great. This has been a nice discussion. I would also like to thank the organizers, especially Katarina Shu, who has been helping behind the scenes during this session today to make sure that things ran smoothly. And yes, please do not forget to consult the website and to register for any other sessions. There are many topics within the ocean acidification research community. So if you'd like to join any of those, you can register on the website, or you can be keeping an eye on the YouTube channel where this session included, but all of the sessions will be posted so that you can look back and kind of dive through these topics more deeply. If you would like to stay up to date with the GOA-ON community, please consider signing up as a GOA-ON member. I will just send that link in the chat. And there is an open call for the GOA-ON Executive Council. So if you scan the QR code, you can get some more information and you can nominate yourself or someone else to join Executive Council. Thank you all. Thank you again to the speakers. And we hope to see you in a later session.